All right, pleasure to introduce Michael Catanzaro from the University of Florida, who will be speaking to us on stochastic dynamics on CW complexes. Thanks, Mike.
All right, thank the organizers for inviting me to give a talk here. Today we'll be talking about some work as a graduate student at Wayne State. So everything I'm going to talk about today is joint work with my tutors, Blagger Church, who is the physics department at Wayne State, and John Klein, who's a mathematician in the math department. So we'll talk about stochastic dynamics on CW complexes. The first thing we're doing is we'll be motivating our definitions. So stochastic processes we'll be considering, if I just were to give you the definition, they would seem extremely ad hoc. So we're going to really try to motivate this from the point of physics, or what is known as Langevin dynamics. And talk about what we're trying to get at, which is a formula for this thing called the current, and we'll describe, or rather I'll say what is called the current. And to solve what we want to solve, we need two pieces, the Kirchhoff network problem and the Boltzmann distribution. So I'll describe all of this in detail classically and in the generalized version on the CW complex. I'll end with the main result, which is a equation result for this current in the low temperature limit. This, again, motivation. So, we're interested in stochastic processes on CW complexes. So we're arising from Langevin dynamics and smooth manifolds. You start with some smooth, compact Riemann manifolds equipped with the Morse function. Function is completely deterministic, so it's specified. The reason why these processes become stochastic is because we take our manifold and we equip it with what is known as a stochastic vector field. So it's a random, or you can think of it as a random walk in the space vector field in your manifold. But to slice, it's a variable which is satisfied these two properties. So by the angle bracket notation, I mean average in the sense of probability theory. So the condition there that the average of Cj is 0 means that it is a mean zero vector field. So average, the value is 0. The piece is the variance of this random variable, and it scales by this number beta inverse time trick at the point in the manifold you're considering at times delta function. So all in all, when you read this, what you should really think is you have a random vector field which is on average 0. Excuse me. Is related in time, so that's a Markov random variable, and with inverse temperature. So we're going to limit when beta tends to infinity, in which case this variance tends to 0, and that's known as the low temperature limit. So to keep that, ultimately we're going to be sending beta to infinity. And if we put the particle on our manifold, well, its motion will be governed by the Langevin equation. So at the time derivative, and you have this equation again is saying, well, motion is determined by a completely deterministic piece, this u of x, which is the gradient of the Morse function. So it's determined by a gradient flow, which is deterministic, and then it's also determined by a stochastic piece, this c, this random vector field. So it's about these two pieces, and so we're interested in what can you say about the long-term dynamics of such a process. Solution to this, excuse me. So a solution to this stochastic equation is then just a stochastic trajectory on the manifold. In other words, it's just a path. So if we place a particle in a manifold and we let it evolve for some time tau, then we can write that by a path of length tau. And now for time, so if we let tau get extremely large, this trajectory is going to wrap around the manifold however it does, determined stochastically. If we wait long enough, we can assume that the trajectory is closed. Now, this is a which I'll justify in a second, but for the time, we can assume that if we wait for a really long time, the trajectory of the particle stops where it started, in which we think of that trajectory as being given a net from the circle into the manifold, and it gives rise to a class in the first homology of the manifold. Brackets A denoting the homology class, and I analyze that by time, by the length of the path. So this homology class, this real homology class that we've divided by time, is known as the average empirical current density, Or in other words, we'll just say for short, it's the average current. So wire the average current. So if you take for manifold to be a circular wire, so you can think of it as being S1 cross D2, then you get these two pieces in very realistic terms. So the function, this deterministic force, is you can think of it as being taking your wire and attaching it to a battery. Whereas the stochastic piece, or the random piece, you can think of it as, well, as the electrons move around, maybe impurities in the wire, maybe they interact with other electrons in terms of phonons, et cetera, et cetera. So now, to actually compute the current from the viewpoint of like electricity and magnetism, you would go spot on your wire and say, you call that cross-section alpha, and you would count how many electrons go by in one direction, and you tracked off how many electrons go by in the other direction. In flux, and you would divide that by how long you've been watching for, and that would give you the honest current. So for electron, you would just take vectory, this describe a circle into your manifold, and you count the section number, it's printed in intersection number with a cross section of your manifold. So that W alpha equals 1 over Tn, where n is the difference of these two numbers, while plus is the number of times the electron goes by in the positive direction, and is the number of times the electron goes by in the opposite direction. You subtract the flux by time, you get the actual current, and so there we homologize the current associated. So the sense in which we will mean current now. So it clearly coincides with the usual electrical current. All right, so what are we going to do new in this talk? People have studied the motion of points. So I put a point on my manifold and I let it evolve. And now instead what we're going to do is, instead of starting with a point, let's start with an embedded submanifold. Say consider a closed D-1 cycle A to naught from N to M in terms of Bordism homology. So if you don't like that language, then you should read this as consider a embedded submanifold capital N into capital M. Or the stochastic process we're considering will be composed of two pieces. The first piece is gradient flow. So if you embed into your submanifold capital N into your manifold capital M, then the gradient flow will push it into a neighborhood of the D-1 skeleton. The skeleton is what's determined by Morse function. Because stochastic vector field is mean zero, because on average it is zero, it will sit in a neighborhood of this D-1 skeleton for a while. It'll maybe fluctuate slightly in this neighborhood, but it won't be very interesting. It'll just sit close to it. Then let's see it's random. It can eventually become quite large, even though on average it is zero. If we wait long enough, there's a finite probability that it can become quite large. And we will push a segment of our embedded submanifold, which no needs to be a manifold, by the way. It's just now you should just think of it as a map in. Put it up against gradient flow, and eventually can cross a critical point. So this is how these manifolds, which no longer needs to be a submanifold, it will just be like a subspace, it can start to evolve and change over time. And look again at the long time behavior of this. So how does this manifold change over time? It's homology class. We divide how long we've been looking for, and we come up with a real D homology class in the manifold. So, I will pictures for all of these things if this is kind of confusing, but remember that this is our motivation at this point. We're not actually going to do this problem right here. We're going to modify this problem and study on a CW complex. So modified on a CW complex, how does the problem change? Starting with a closed manifold, we'll just start with some integral -1 cycle. And for the rest of the talk, when I say CW complex, you're more than welcome to just stick with the word simplicial complex if you like. I will treat simplicial complex. So now we have initial D-1 cycle. That should be thought of the initial condition to the stochastic division. And will evolve deterministically according to this space script M sub x, which I have not yet defined. But you should think of it as just the discrete log of a Morse function. It doesn't exist, though I should warn you, of discrete Morse functions. It is so this D minus will sit in D minus 1 skeleton of our CW complex for a while. And now on longer time scales, this random vector field will push this D minus out of the D minus 1 skeleton, and it can pass across a cell of dimension D. And so now evolved for a long time, and we see what is the homology class for a long time. Ultimately, what we're interested in. We're interested in a formula for the average current for long times, or in other words, stated differently, we're interested in a formula for this homology class, for this time averaged homology class, which represents the long time dynamics of this stochastic process. So at this point, pictures and kind of try to get in some maybe better intuition for what's going on. The one-dimensional case. So on the top of the picture, I'm looking at a one-dimensional manifold, and are determined the Morse function. So I'm actually doing the graph of the Morse function of a one-dimensional manifold here. So critical points at I, J, K, alpha, and gamma. The critical points of index 0 are I, J, K. The critical point index 1 are alpha and gamma. And then I have the corresponding CW, or simplicial decomposition of the manifold as determined by that Morse function. So the critical points of index 0 give rise to 0 cells. The critical points of index 1 give rise to 1 cells, and et cetera, et cetera. All right, let's try to compare this situation to a random walk on a graph. So what do I start with going somewhere on the manifold? And initially, what's going to happen is that point is going to fall down to a low minimum as the gradient flow. So the flow eventually will initially push the point down into the minimum at I. And on the associated CW complex or simplicial complex, you're thinking of, well, I have a point, or I have my particle is sitting at node I, or vertex I. And so it will just sit and maybe fluctuate slowly in this well near I. But now it becomes large enough. If it becomes large enough, it can actually push this cell, this cell out of the well, and start to move up towards alpha, towards the critical point. And if we would see this random vector field again, it can become large enough that eventually it gets close to alpha and cross the critical point at index 1 at alpha. So one critical point, there's nothing special needed about the noise at this point, and the flow will now push it down into J. So that entire process happens instantaneously on the associated simplicial complex, but takes some time on the one-dimensional manifold. All right? So this is a way of thinking of random walks on graphs. You have waiting times at the vertices. You can think of this as, well, you had an associated manifold, and it was the juice on the vertex corresponds to waiting for C to become large enough so that you cross the critical point line to the edge that you jump over. One more thing I'd like to point out that maybe seems trivial at this point, but again, it's important for what we're going to do in higher dimensions. If I look at transition on a simplicial complex, go from state I to state J, I get the boundary of the edge that I jump across. We have alpha that's given by J minus I, and so J is I plus the boundary of alpha. On a graph, or one-dimensional CW complex, it's a very real statement, but that is going to motivate transitions in higher dimensions. All right, so one dimension, we can picture. So if you're a one-dimensional manifold, yeah.
Can we go to the last picture? So,
sure.
Shouldn't the height of alpha, shouldn't we think of that as having some sort of an effect here?
Absolutely.
How do I see that in what's described
so
there?
in what I've described so far, you won't see that. Height of alpha will determine the rate at which the particle jumps from I to J.
Okay.
So you can imagine how if the particle is sitting at J, it's more likely to go to I than it is to K. The rate at which the particle will jump to I is greater than it, because it's easier to cross the barrier at alpha than to cross the barrier at gamma. So think of them. They will give rise to the rates, but I haven't described that at all yet.
Okay.
Sure. Time, please ask questions, because I understand like maybe a new way of thinking about stochastic dynamics in higher dimensions. So on the two-dimensional manifold, consider the following picture. So here at, let's say, here A, we have a critical point of index 2 marked by alpha, and suppose along the boundary we have two critical points of index 1, say I and J. So in the manifold picture, your cycle consists of, let's say, I plus J. And stochastic vector field can push part off of I, like as you see in figure B, and the cycle can start to move up towards alpha. And eventually it will cross alpha, and it folds over and it doubles up on D. So the cycle here is now changed to being, it was the cycle I plus J, and ends up at the cycle 2J. So before I move on, let me just make sure that that's clear. So, yeah, the cycle starts as I plus J, and it ends as the cycle 2J. And the way that you can go from I plus J to 2J is you add the boundary alpha. All right, so again, a transition run walk, like in higher dimensions, on a higher CW complex, we're putting a cell to jump over, but a cell to jump off of. In this case, the cell alpha, you jump off of the cell I. You can maybe more complicated picture. Say your CW complex, in this case, the torus, and the cycle on the right-hand side of the torus is your initial condition. So we start with some initial cycle. We randomly jump across two, in other words, squares or rectangles in this triangulation, or not a question, but in the CW structure. We'll jump across two cells, and when we get to jump off of one cell, so we will remove one cell and we will add to it the boundary of the corresponding two cells. And so this time in the back of the torus, you think of as well, the Morse function in this case is just by rotating. So in general, most of the cycle is rotated backwards, but there is some deterministic, there's some rather stochastic piece. See, part of the cycle jumps ahead, part of it lags behind, but at all times it's still a cycle, and generally speaking, it's moved towards the back. And so these are the processes we want to study, and this is what we want to make rigorous now. So, briefly, what is the stochastic process that we are considering? So, initial data is to fix a minus one cycle, an integral d minus one cycle on your CW or simplicial complex. And it consists of d minus one cycles, real d minus one cycles, which are get to the initial cycle, state space, and a transition between two states. So the transition from cycle D to cycle D prime consists of requires two pieces of data. The first is a D cell alpha, and the second is a D minus one cell I. So the new cycle D prime is D plus some appropriate times the boundary of alpha. All right, so the types of processes we are considering in higher dimensions. And which I would say that this is from maybe other generations of random walks on graphs to random walks on special complexes is visible here, and that is in the state space. So, for example, people like Shaya Mukherjee, Rowe, Carly Clark, they studied random walks in higher dimensions where the state space consists of cells. So you start with a D-1 cell, and you jump to a different D-1 cell over a D cell alpha. In this case, space is cycles, so the state space is huge in this. It's large. We're using this definition is because this is motivated from physics. So this is all about this notion of Langevin.
Sorry to interrupt you. No, there seems to be some sort of difficulties. Is anybody else getting that audio connection?
Yeah, I am.
Yeah. No, apologies to everybody. I'm not sure why this happened. Do you want to try maybe off your audio and then turning it back again? Sure.
Can you hear me?
Oh, better.
Okay. Sorry about that.
All right, is everybody else hearing that better?
Is this good? You hear me?
Yeah.
All right, okay. Hopefully that'll stay better. All right, thanks. Sorry about that, everybody.
Yeah, no, let me know if it happens again. So yeah, I was saying was this is a part where this maybe differs from what people have considered before. All right, so pictures, you notice that if the Morse function is fixed, then actually what's going to happen is the part, or in this picture here, the one cycle, will tend to some configuration of minimal energy, or it will to some configuration of smallest weighting. If I go back, and you look in this picture, if we were to watch this for a long time, eventually the particle is going to jump back down to I. With probability 1, it will eventually go back to I. There. So what you want to do when you consider these processes is you want to let the Morse function vary in time, or stated differently, the rates which define this stochastic. You want them. If you don't let them vary in time, then the particle or the cycle mesh will actually find this of smallest energy, and it will be there with overwhelming probability. The transition makes it will transition back with probability 1. So moving forward, we study the set of parameters. So for the rest of the talk, let's fix a connected CW or simplicial complex of dimension D. So now parameters consist of the real vector space of just assignments. So D minus 1 here denotes the set of D minus 1 cells. And so E just associates a real number to each D minus 1 cell, and W associates a real number to each D cell. So the discrete version of the Morse function in the continuous case. This E and W need not satisfy any conditions, so this is not, in general, a discrete Morse function. These will be the numbers to determine the rates of the stochastic process. So if in the case of, let's say, like unbiased fusion or pure diffusion on the manifold, or complex rather, you would E and W to be identically 0, which is absolutely something you can do throughout this talk. And in general, when we vary our parameters, we'll do it in a periodic fashion. So the driving protocol will be a smooth path in the space of parameters, which is periodic. So we take a path of parameters, so we're going to let E and W vary in time, but there exists some number tau D, so that after I go along path tau D units, I'm back to where I started. And the specific path of length tau D is equivalent to what's known as a Moore loop, if you know what it is. It's not exactly in there. So I'll write down maybe something a little bit more rigorous. Let's extend these operators, this E and W, let's extend these two operators on the chain complex. So this assigns every D minus 1 cell a real number, and we can map that to the chain complex by sending any D minus 1 cell x to e to the base of x times x, where e sub x is just the value. And a fixed real number throughout this thought of this inverse temperature. We can do the same thing for W, and then these operators, this e to the beta W, we can use to define modified inner products on the D cells, on the D chains and the D minus 1 chain. So they're given there. You feel like this modified inner product, and you can just skip that line, and you can just move on to this one. The point is, to those modified inner products, the adjoint of the boundary operator on the chain complex is given by exactly this composition. So by e to the minus beta W boundary star e to the beta e. So you should think of this star W as a bias gradient operator. And if I take W 0, then it's precisely the gradient operator. A discrete version operator, I should say. Now that we have, like, the E and W will help form the rates of our process, and so you have we can know what is known as the dynamical operator. The dynamical operator is an operator from the D minus 1 chain to itself, just given by this composition. So be reminiscent of a Laplace-Beltrami operator, if you'd like. It's like a biased Laplacian. Because I mentioned we don't have the other piece, we don't have the boundary star boundary component, but dynamical operator, and you should think of it as a Laplacian. The dynamical equation is the following equation. So we start with initial conditions. In other words, we start with an initial cycle, and periodic driving protocol, or in other words, periodic way of varying the rate, these E's and W's, and some And then what we'd like ultimately, or we're hoping to do here, is to solve this dynamical equation. In other words, solve that dt is h applied to rho. So rho here is a one-dimensional family of d minus 1 chains of x. So rho you think of as a distribution. It is not an honest distribution. It's not a probability distribution. But you have d minus 1 chains in x. So rho is the trajectory that we're after. All right. Is there any such a problem like this? It turns out that there is. If you draw slow enough, meaning so exists some tau 0, when tau d is greater than tau 0, a periodic solution of the equation will exist unique. So this is saying that if I vary the rate slow enough, if I vary E and W on my d minus 1 cells and d cells, if I vary them slow enough, then this equation that we just saw on the previous slide will have a solution. It will be unique. Good. In this formal solution, we can find the average current density. So the density would just be given by applying the bias gradient operator to the solution rho. And then finally, the thing we're after, this long-time behavior, this homology class, is given by Q. It's where we integrate this current density period. Right, before moving on, let me just say the following. Point is a formal solution to a differential equation, namely by the theory of differential equations. We're just conceding a solution. One dice slow enough. Sort of this homology class given by integrating by W star of rho, it's just a full expression. So it's not computable at all. So the remainder of this talk is formulating this problem so we can come up with a solution which is extremely computable. So the idea of being able to write this current density J right now is completely formal in terms of the Kirchhoff network problem and the Boltzmann distribution. So what we're interested in. So I'm a formula for this. So before we do that, rather, let me just say if X is the graph, this problem has been solved completely by Cherniak, Klein, and Sinitson. So the parameters generically, well, then write down a nice expression for Q, the current, this long-time homology class that we're interested in. And first, you take this if you take the low temperature limit, so we sum in our stochastic process to 0, and you take the adiabatic limit, which is the limit in which tau d goes off to infinity, so you vary the parameters infinitely slowly, then the error actually quantizes. It's an interesting result. It has implications in statistical mechanics. People have used this to study problems in like molecular ratchets and molecular motors. Very into any of that, but there's lots of really interesting stuff you can read about that if you're interested. As I said on the previous slide, the point is that this Q that we're interested in computing by this theorem on graphs, it can be written as an input of a complement of two things. So K, which is the solution of the network problem, and OB, which is the Boltzmann distribution. And it presents a sum over spanning trees, and rho B written as a sum over vertices. So this is the slide that we're really going to generalize to higher dimensions. So what all of these things mean, and then we'll talk about how you can combine them to get a solution. What is the network problem? So the network problem for a CW complex X consists of constructing an orthogonal splitting of the boundary map. You want to suspect to the modified inner product that we introduced earlier on the D chains. So, Schubert sequence, which is very fundamental to algebraic topology, I would say. And to solve the network problem just means to construct a splitting of that. So let's see what is that. So we went from the D-1 boundaries to D chains. So I compose the two. So if I do this map that I want K, and then I take the boundary of that, I should get the identity. So that's the splitting of boundary. The condition is that it be orthogonal with respect to the modified inner product. Or namely, if I look at the value of K on any boundary, take the product of that with any cycle, I'll get 0. So these two conditions might seem funny. You might ask, now, why are you associating the word network problem to this seemingly, purely algebraic topological question. The reason if this is a graph, then two conditions are equivalent to what is known as Kirchhoff's laws. So that boundary K is the identity on a graph is interpreted as the sum of currents going into any vertex is the sum of currents flowing out of it. And the second the value of K over any cycle with respect to the modified inner product is 0. Well, I'm saying K here is the current. So when I look at it, if I look at KB in the inner product with the modified inner product W, W is playing the role of resistance, and so current times resistance gives you voltage. And so the same condition is really saying that the voltage drop over any loop is 0. So this problem is equivalent to solving what you could say are Kirchhoff's laws in higher dimensions, or satisfying Kirchhoff's laws in higher dimensions. Kirchhoff actually did this for graphs. He wrote this down using spanning trees on the graph, or spanning trees on the network. So, and with a higher dimensional notion of a spanning tree. So before I go on, I should say that many people have done this type of generalization, which I'm about to do. Not all of us, not all of the people who have done this use the same definition for spanning tree.
So before on, could you say how this approach differs from like Hodge theory? Like splitting differs from what you get doing Hodge theory? So combinatorial Hodge theory says that such a splitting should exist, but here we're trying to be explicit about it. Something about that now, but I think the connection to Hodge theory might be clear when we talk about the Boltzmann distribution. But Hodge theory says such a splitting should exist, but here we're going to explicitly construct it. Spanning tree in higher dimensions is the following. So it should be subcomplex. So the D complex integrally should be 0. So this is the condition that there are no loops. It should be that it has the so in dimension D minus 1, the Betty number of our complex D is the same as that of X. Finally, the last condition is kind of like a normalization condition, and that's that you contain the D minus 1 of X. So this reduces to the classical notion of a spanning tree. And again, men have generalized the notion of a spanning tree, right? So there's some papers by it. So Lines, for example, Duval Ivins, many people who have generalized this, so this is just our version of that. So now that we can construct the split, the D spanning tree T of X, we can define a linear transformation from the -1 boundaries of X to the D chains of X. How do we do it? Well, boundary in X, there's a chain in the tree T whose boundary is the boundary that you started with. So this is confusing, but again, if you think of on a graph, this is just a statement that boundary on a graph, a 0 boundary, consists of just, let's say, a difference of vertices. And tree, in a spanning tree on a graph, there's a unique path between those two. And this is just the exact statement in higher dimensions. Given there's a unique D chain in the tree whose boundary is the two things that you started with. Or in boundary, it can be general. You not only have two. So these are the tools we use to construct the splitting, but unfortunately in high dimensions we have to be a little bit more careful. So I mean we have to weight these areas appropriately. So weighting turns out to be the order of the torsion subgroup. So you should the order of the torsion subgroup of the tree in dimension D minus 1 of the tree to be this positive real number. So by the torsion group squared, and then you take a product of all of the weights of the D cells in the tree. So the D cells in the tree, this product, you should think of as like the product of the resistances of the edges. On a graph, precisely what it is. And in higher dimensions, a good way of thinking about it as well. And notice if X is a graph, this theta number is 1. So you don't see it in the classical setting. It's something which is always in higher dimensions. But now pieces, we asked this is the sequence we wanted to split, and now we have the following here. So with respect to modified inner product, the desired orthogonal splitting is given by a weighted sum of each of these individual operators. So the idea that
you have a way of lifting D minus 1 boundary to X, but that choice, picking a tree is picking a choice, and so you want to sum up over all the different choices, sum up over all the different ways you could have lifted it, and be a little bit careful when you sum them. You need to weight them appropriately so the formulas work out right. So the splitting is actually a splitting. It's orthogonal. So this, so that's solving pure problem on CW complexes in higher dimensions. And again, this form, in this way, written like this, we were the first maybe to say, but it has appeared in many other contexts, especially the other authors that I previously mentioned, all of this formula written down. So this is not new. All right, so the second thing that we needed to generalize was this thing that I was calling the Boltzmann distribution. So it might be easier to see that from the viewpoint of algebraic topology, and it deserves to be called the Boltzmann distribution if we phrase terms of this problem. Studying the combinatorial Hodge problem. So what is the you pick homology class, some real homology class in degree D minus 1, say, so I call X here, is to find a harmonic representative for that class. We will find a cycle which represents the homology class that we started with. So in other words, it's closed, but also co-closed. So that means, and with respect to the modified inner product, or namely, that the modified adjoint applied to it is 0. Right? So to say that a cycle means that the boundary of rho is 0. So getting that not only the boundary of rho be 0, but that boundary star of rho also be 0. So this is called the combinatorial Hodge problem, because this cycle rho will become the unique harmonic form in the homology class specified by X. All right, so just as with the Kirchhoff problem, we can trying to solve this problem in terms of a splitting of a short exact sequence which shows up all the time in algebraic topology. And this is the short exact sequence which defines homology. So the solution to this is an orthogonal splitting of the projection map in this short exact sequence. So, right, the splitting says that rho should represent the homology class, and the fact co-closed, which is the modified inner product, says is orthogonal to any boundaries, any of the D minus 1 boundaries. All right, construct such a splitting. What's called a co-tree. So this is dual tree, and this of homology, rational homology. So its one span co-tree is just a subcomplex L. The inclusion, so J cell here, includes an isomorphism in homology, and this one homology references the other two conditions just as before. You think of spanning trees and co-trees. So some tree has no homology of X, and a co-tree is dual in the sense that in its top dimension it sees all of the homology of X rationally. Dual, and that's why we're calling these co-trees. I think Simon and Martin call these relatively acyclic complexes, and if you language of Matroid theory, this is a complement of co-base. So with that language, that's all of the span co-tree.
Yes, sir.
Yeah.
We seem to be audio trouble again. We'll try this thing to connect your audio since it was helpful last time.
Sure.
I'm not sure why this is happening to us today.
Hear me?
Yeah, that's fine. If you turn down your volume, that probably couldn't hurt as well.
All right. So a great maybe thinking about these, in fact, because for a graph these are just vertices. And you can on let's say a 2 complex, you can try and see what they need to be to work out what these should be. But we will use these to construct this desired splitting. We'll use trees to come up with that we like. So as a co-tree is a dimension D minus 1 object, it doesn't have any D cells, which means that from the D minus 1 cycles to the homology in D minus 1 is an integral isomorphism. It's an inequality. So the one homology of our random code tree, it maps to the d minus 1 homology of x and find that map to be phi L. These code trees acquire rating by taking the co-kernel squared and multiplying by what you could think of effectively as the resistances of the cells in the code tree. I should say this co-kernel will be finite. We're assuming that the right-hand vertical map is a rational isomorphism. So, all right, great. So we can kind of assemble these to form the split. So phi is a rational isomorphism by the definition of a code tree. We can invert it rationally, and we can consider this composition. So the homology maps over to the cycles. That's the map that we just inverted rationally. The map to the cycles in L maps to the cycles in X. And so now this gives us this composition psi L. So again, what this is saying is that for each code tree, you have a way of constructing this preferred cycle representative. That's what the map psi L does. And sum over all of the different code trees, or sum over all the different ways you could lift the W class to a cycle representative. And so the statement is here. That is given by this weighted summation formula. And now the only say, maybe if you're not so interested in stochastic dynamics, but if you're in other applications of topology, is that this formula gives you a canonical way of lifting a homology class in a CW or a simplicial complex to a cycle representative. So I think it's interesting in that perspective outside of this setting, because say you were studying homology and you had a homology class and you want to see, well, where does that live in the data, or what is a preferred representative? In fact, this sum psi here would give you a probability distribution because it's normalized for the set of all cycles which could represent it. So we get the Boltzmann distribution. The Boltzmann distribution is simply given by taking this weighted sum that we had on the previous slide and just applying your homology class to it. So SAR is the homology class that you were interested in studying. So I'll list that to a cycle representative. You weight it, and then you sum over all the possible liftings. Okay, again, why is this called the Boltzmann distribution? Well, if I take a simplicial complex to be a simple graph, and code trees are simply vertices, and all these torsion, all these co-kernel factors are 1. So it's become 1, and the co-kernel becomes 1. So the weight is just given by e to the minus beta, this factor before. So this formula turns into this sum that you see at the bottom of the slide, which is the classical Boltzmann distribution. Governs particles are distributed with respect to energy. So thinking to it is the Boltzmann distribution. And you could say the unique harmonic representative in any homology class. All right, so now 2 pieces that we were interested in, and we can see how do these fit together to form the solution that we were interested in. So the proof is that if you take limits, so again, I slowly change the parameters of my stochastic process, then this full thing, which we couldn't do anything with, equivalent to, instead of integrating this formal solution, integrate this to the Kirchhoff network problem applied to the time derivative of the Boltzmann distribution. So this simplification. So I didn't include proof of this because it's just very straightforward. In the sense that applies formal properties, and both of these expressions satisfy those properties, and it must be unique. So have this nice formula for the long-time average, the long-time distributed stochastic process. And this we can try and come up with a quantization result, which we'll in fact see in a second. So if I get the function which weights the d minus 1 cells is injective, then in the low temperature limit, this Boltzmann distribution will tend to it'll be supported on a single code tree. So the point is that if E is an injective function, then this distribution will have like a unique minimum. And the point is that this is tending to that unique minimum. Anything is true for the function W and the Kirchhoff, the solution to the Kirchhoff problem. If the function is 1-to-1, well then it will have unique minimum, and there's some unique tree. There's some tree which has smaller resistance or smaller energy than all the other trees. And so pieces together, we get a result. If we view generically, then in the temperature adiabatic limit, we get a rational homology class. So just to read, what are these two limits? So the limit of tau t going to infinity is slower variation of the parameters of the numbers E's and W's that we've attached to the cells of our complex. And tending to infinity is the low noise or low temperature limit, which we're kind of like killing the stochasticness. It's not the same thing, it's equal to infinity. There is some noise, but it's infinitely small. And so kind of result, or why should you expect such a result to be true, is the heuristic holds. If you're interested in computing average current, you could think of the limit of the process in the following. So you have some initial cycle, tend to some minimal co-tree up. Or if we were looking at a graph, this is the statement that our initial cycle fell into a zero. It falls into a local limit, in other words, a critical point of index 0. Remember that thought of as vertices. So this is this analogy is made. Cycle falls into some initial co-tree, to a different co-tree through some unique tree T. It's just like a random walk on a graph. If you have your particle sitting at some vertex and it was going to go to a different vertex, well, it would travel across the minimum tree, the tree with smallest resistance. So that's the higher dimension. Now, we'll sit at some point in time, and this process will just keep repeating. I would say that on a graph, the random walk, the particle vertex to vertex across these minimum trees, and it mentions the similar happens. It jumps from co-tree to co-tree across minimal trees. So, yeah, so this is what is happening with that. This is the long-time behavior of this homology class that we're interested in, and this is what has higher dimensions. So I will stop there.
Questions? Could you give us some, actually, can you set your audio while I ask my question again? I don't know. Yeah. Turn down your volume even further if that's possible, so you can still hear me. So, trees.
Yeah.
Can you maybe give us like a couple of examples of that? So
co-trees are kind of hard to define. Actually, not hard to define, but they're not so intuitive as trees. So, sorry, here it is. So first of all, if X is half, a co-tree is just a single vertex.
like a simplex or something.
So X consists of a simplex. Then let's say it's like a two simplex, so I'm thinking of a triangle. Then here, a one tree would be any two edges of that two simplex and themselves. The two simplex doesn't have any homology. So what we could do here to construct a co-tree, for example, is we put the d-1 skeleton, or in the picture of the two simplex, you would start with the one skeleton, and you do this until this map here, this JL star, becomes an isomorphism. The simplex, right, it has a copy of H1, and so if I knock off any edge, I will get a copy. I'll kill that cycle. And all co-trees arise in such a fashion. You start with a skeleton, and you just remove cells which are on homology classes. Other than that, really a great.
All right, so for more generally for a simplex, a co-tree will be a horn.
Yeah. Exactly.
Thanks.
Yep.
Any other?
Excuse me. What is spanning a definition?
It is this definition on the Betty number. So that the codimension 2 Betty number agrees with the codimension 2 Betty number of X. You can't really see it. But that spanning comes from. And, kind of I included the word spanning here because these are dual to higher dimensional versions of spanning trees.
Got it.
That's what appears here, but yeah. Sure.
Involved kind of summing over these code trees.
Yeah, precisely. So the point of each code tree, just if you take some of the diagrams I just wrote down a second ago, based just definition of a code tree. So each homology class will have a unique cycle representative within the code tree. So homology class in X, and each code tree I can list it.
Code trees.
So
And this is the code trees.
for an individual code tree. So for an individual code tree, I can list each homology class. Basically, just look at this definition. If I'm looking at this one homology, this max R is an isomorphism. So for each code tree, I can list it across this isomorphism. But now you want to sum over all the different choices, or sum over all the different lists that you could make. So but for that psi L is making precise the notion of bringing across this isomorphism. And that's why you have the summation here. The summation of tau L psi L is the weighted sum of all the different lists of your homology class. So in statical lifting, because the sum can be kind of big, but it's, yeah, I was canonical, so that's a nice thing to have.
All right. Any other questions?
So you mentioned earlier, maybe like a bit more about the connection to persistent homology, because you talked a little bit about probability distributions and sort of how do they track.
Yes, the audio again is horrible. Let me try resetting my second here, like any of your questions. Sorry.
Here.
Yeah.
I think like at one point you mentioned very briefly the connection with persistent homology and some distributions. So like, could you maybe say a couple of more words about that?
So, what I was referring to is actually this slide right here. So, I'm just saying, this sum here gives you a canonical list of any homology class. So, if you have a simplicial complex or a CW complex, this sum here will give you a canonical list of any homology class to a cycle representative.
Mm-hmm.
So, this is kind of big, but it is normalized. There's this normalization factor in front of it, this 1 over tau. You could think of this, I mean, it is precisely this. It is a probability distribution on the all cycle lists. So it's kind of a heat map, if you like that language. And the only mention persistent homology is because it might be convenient. I mean, you might be interested in lifting, like a homology class, right? Some barcode that you got from some calculation, and now bring it to somebody who gives you the data, and you can show them that. And if they're not a mathematician, homology won't make much sense. But it was some kind of like an fMRI picture, let's say. Once you look at the homology class of the cycle, you could point to it in the image and say, okay, well, most likely with high probability the cycle is sitting in this region. So I think you actually, Sarah, posted a paper recently on this. Skeleton, and very much related to this summation that's right here. This sum, I'm using code trees, I believe you call it spanning trees, which if you don't have any homology, the homology of the space is in a certain range, then the tree code tree agrees. So that was all meant. Nothing here persists. I'm just saying for a given like this life, if you like, you could get a cycle life.
Mm-hmm. No, it also seems because there's another paper that Primoz just posted, Primoz Krabbe, and I think Yogeshwaran, and it's like like in early January, I think, and like they're looking at basically like they're also looking at these A cycles there. So I thought like it seems that this is sort of a thing right now.
Yeah, I haven't seen it, but I will look at it. That sounds interesting. It seems like, yeah, this stuff is kind of maybe gaining traction lately. I don't know.
Yeah.
Thank you.
Thank you.
Mhm.
One more time. So thanks a lot, Mike.